So we will start the first session of the second day of ATAL FDP on earthquake safe design and construction practice. It is organized by Applied Mechanics Department, LD College of Engineering, Ahmedabad. Under this, LD College of Engineering is under the Director of Technical Education, Education Department, Government of Gujarat, and we are conducting this FDP under the aegis of AICTE Training and Learning Academy, ATAL. And today's first session is on understanding structural behavior through experiments in earthquake engineering. In the last lecture, we talked about various conventional lateral load resistance systems, column, shear wall, bracing systems, MR frames, tubes. And yesterday, we have said that this is a MR frame. They are lateral load resistance. These are the pictures we have seen yesterday. These are the braced frames where we are providing the bracing to increase the stiffness. This is the X brace, this is the chevron brace system, eccentrically braced system. Such kind of system is provided when you want an opening here. Right. When there is no need of opening, you go for the X bracing. Right. So here you can see the bracing. You can see the bracing here. This is the bracing system, and the purpose of the bracing system is to increase the stiffness. This is the shear wall. Shear wall is a concrete wall. Concrete wall means it is also reinforced, and when the purpose of the shear wall is also to increase the stiffness. And when the lateral load will act, we are knowing the earthquake force is distributed as per the stiffness of the vertical element. So if the stiffness, you see, if you look at this width of the shear wall, the width of the shear wall may be 2 meter, 3 meter. So as compared to the column, the stiffness of the shear wall is very high. As the stiffness of the shear wall is very high, it is going to take most of the earthquake force. Right. So the shear wall is one of the most important element in our system. Right. Then this is how the construction of the shear wall is taken place. We have discussed yesterday. You can see the pictures of construction of the shear wall, right? Shear wall constructed, and then we talked about the dual system. Dual system means you see, only shear wall will not work. So generally, we are designing moment resisting frame. A moment resisting frame is a moment resisting RC frame we are talking about. It is quite flexible, right? So basically, yesterday we discussed that the deformation is one of the main criteria. So you have to resist, and the shear wall will give you the stiffness, and the shear wall will also resist the lateral load. So the load of the column means I'm talking about a lateral load. Lateral load on the column is shared by the shear wall. Right. This is the construction, and then we talk about the tubular systems. These are systems, but we are not going to discuss this part. But now, you see, today we are going to talk about the understanding of structural behavior through laboratory experiments. So, question will arise: why this earthquake lab is required? So, after huge earthquake of 2001. As far as Gujarat is concerned, a high-level committee was formed under the chairmanship of Chief Minister Narendra Bhai Modi. The committee has identified numbers of reasons for the devastation in Gujarat. They have listed out more than 100 reasons for the devastation. And one of the reasons identified was that the absence of the subject of earthquake engineering in the UG curriculum. This subject was, the earthquake subject was not that in the curriculum of BE Civil. That was one of the reasons they identified. And you see, we have worked a lot after 2001 Bhuj earthquake. Almost 800 buildings we have actually visually inspected. And we find out the whether these buildings are having a significant damage or not, whether people can use this building without repairing or retrofitting or not, right? So you see, we came across numbers of structural engineers, civil engineers at that moment, and we find that these civil engineers or the structural engineers, they are not knowing the concept of earthquake engineering, right? So they are very good as far as the design of structures for gravity loads are concerned, right? But when we have to design the structure for the lateral load, how the lateral load is distributed. So the basic difference between the gravity load distribution and the lateral load distribution is gravity loads are distributed as per the tributary area concept. It means the column in the center will receive more load. But it is not the case as far as the lateral load is concerned. The lateral loads, the lateral load due to earthquake is distributed as per the stiffness of the vertical element. If the element is more stiffer, it is going to receive more load, right? And if your element is flexible, it is going to receive less load, right? So remember this: the lateral load due to earthquake is distributed as per the stiffness of the vertical element, right? And this understanding was not clear as far as the civil engineers or structural engineers are concerned before 2001. And the main reason was the subject was not there. And then earthquake engineering subject was introduced in 2003 in the semester 7 compulsorily. Now it is introduced, but again, what is the problem? The problem is the behavior of structures under earthquake forces is very complex, right? So therefore, to understand the structural behavior under earthquake force, not only theory lectures is sufficient, and therefore there is a need to develop an earthquake lab. And at that moment in Gujarat, not a single earthquake lab was there. And therefore, we had taken up the task that we are going to develop the earthquake lab. Now the question is, when it comes to the earthquake lab, then the expenditure of developing earthquake lab is most of the time in crores of rupees, right? And suppose if I ask any institute to develop a earthquake lab which is costing maybe 1 crore, 1.5 crore or something like that, then those institutes will not develop because of the limitation of the funding. And therefore we say that if we develop a very low cost earthquake lab setup, then people will purchase this laboratory setup, right? And we start working in that area. So we started developing a earthquake lab, right? So if it is explained through experiments, then it will become very easy to understand the behavior of the structures and the concepts of earthquake resistant design or the lateral load distribution. It will be very easy, and that's why this earthquake lab is needed, right? If we talk about the earthquake, basically it is a random strong ground motion, right? And you see, earthquake carries different frequencies all the time, right? At one moment the frequency is 8 hertz, next moment it may be a 10 hertz, it may be 20 hertz. So the frequency carried by the earthquake is constantly changing, right? And similarly, as the external excitation is changing, and therefore the response of the structure is also complex, right, to this ground motion. And when it comes to the analysis of structures for forces, then we have to carry out, basically it's a dynamic force, so we have to carry out dynamic analysis. But for the simplification, the code has given a static procedure also. But earthquake is a dynamic load, so you have to carry out dynamic analysis. And this IS code, IS 1893-2016, it has given a procedure for the dynamic analysis, but at the same time, code is saying that If the engineers are not doing dynamic analysis, a very simple method, a static also given. It is known as the seismic coefficient method, which is given in the code. It is a basically code-based procedure, very simple procedure. No dynamics is involved. But when you analyze with this, it is more conservative. More conservative means you get the result. It will be on a higher side, right? So when you design for these forces, your structure will not be economical. When you carry out a dynamic analysis, I think you are optimizing the structure, right? So the code has given both the options. If you are good enough in dynamics, then go for the dynamic analysis, and it will be good, and it will give you economy to the project. And suppose if you are not doing dynamics, then go for the static procedure. That is the seismic coefficient method. This is a code-based procedure. Follow that, but it is conservative, right? We are knowing that earthquake forces are much larger as compared to the design forces. Yesterday I told you, a 100 kilonewton force is coming on your structure because of earthquake. We are only designing for 20 kilonewton, 30 kilonewton force. That's all. We are not designing for the full level of earthquake force, and that is the reason that the experiment will become very, very important. Design philosophy is saying that collapse is not allowed, damage is allowed. So we talk about the inelastic deformation. That is the added point. As far as RCC design at undergraduate level is concerned, we are not allowing any sort of damage for the gravity loads. But if we design our structures for the earthquake, we are allowing damages. Collapse is not allowed, right? So laboratory testing of a physical model to earthquake simulation provides a practical aspect to the complex behavior of the structure. So this setup will help in making us understand to behavior of structures, and how to shake the structures. So for that you need a shake table, right? Shake table. So as far as the laboratory testing is concerned, we are directly going to this part. We are going to perform dynamic test of the model. So there are two types of test, three types of tests. A free vibration test. The free vibration test means only the initial disturbance is there. You are disturbing the system initially, and then the system will vibrate on its own elastic property, right? That is a free vibration test, right? And what is the forced vibration test? In case of a forced vibration test, we are applying the force during vibration, during the once the vibration starts, once the shaking of model starts, we are applying force during the vibration, right? It is known as a forced vibration test. So what is the difference between the free vibration and forced vibration? The free vibration test, only the initial disturbance is there, while in the forced vibration, during vibration we are applying the force, right? This is a basic difference. And the third test is basically ambient vibration test. Now in ambient vibration test, what exactly we are doing? You see, we are not performing any test, but we are putting the sensors in the building, and when a movement is taken place, when anybody is moving, then the small vibrations will be created, and this small vibration will be picked up by the sensors. And you see, when you don't have any constraint as far as your structure is concerned, you are not putting any constraints on your structure, then your structure is going to vibrate in the natural mode. And if we go for the ambient vibration test, it is very simple. You have to put the sensor, and if any movement is taken place, vibrations will be created. This vibration will be picked up by the sensors, and it will give the natural frequency of the system, right? So this is ambient vibration test. So if we talk about the free vibration test, it is of two types. Initial displacement test, it means we are disturbing the system, right? And then we are allowing it to vibrate, right? It is an initial displacement test. So displacement is given, and initial velocity test. Initial velocity means we are giving the impact, right? Displacement is not given, but the velocity is given, right? And as far as the force vibration test is concerned, there are numbers of tests. You can see the resonance test, variable frequency, sinusoidal excitation, transient excitation, vibration table, shaking table test, quasi-static loading test, pseudo-dynamic test, real-time dynamic hybrid test. I'm not going to talk about all this, but today we will talk about this test. One is a free vibration test, where we are going to have a initial displacement test, initial velocity test. Then we go for the resonance test, variable frequency test, and test, right? So this is, scope for as far as today's session is concerned, right? Now, what are the requirements in the laboratory? What exactly we want, right? What exactly we want? Basically, three things we require. The equipment which is required to provide a dynamic force. Dynamic force means we need a earthquake simulator, shake table. We need a shake table. The shake table will shake the structure of the model, right? Second is we need a model, a prototype or scaled or experimental model. It may be anything, right? It depends on the facility available at your lab, right? So it may be a prototype, it may be a scale, it may be an experimental model. And third, you see, the shake table will shake the model, so your model is shaking, so you have to catch the response of your model. So you need a instrumentation setup. So to measure the response of your model, you require a sensing unit and data acquisition system, right, to take this data. So actually we need three things. One is shake table, second is model, and third is instrumentation setup. Right. Now, what is shake table? Shake table is a laboratory equipment which is capable of reproducing the motion of the ground during an earthquake, allowing for the control testing of the structure subjected to earthquakes. So the shake table are such that they actually produce the real earthquake motion, right? And what is the degree of freedom? Is a 6 degree of freedom, right? 6 degree of freedom is you can introduce as far as shaking table is concerned, right? And complex servo hydraulic system which is capable of producing the actual earthquake, right? We are going for the prototype or scale models, right? And this shake table test will help in investigating both linear as well as non-linear structural behavior, right? So it will help in both the things. Now we look at the facilities available worldwide, right? If you look at this is the shake table. Means it's the earthquake simulator of University of California, Berkeley, right? Now you look at the setup. The setup is so big. This setup is so big. This is the shaking table. This is the shaking table, right? And if you look at the specification, the size of the shake table is 20 feet by 20 feet, and the payload capacity is almost 1 lakh pound. The servo hydraulic actuators are there. It is horizontally driven by 8 actuators, vertically by 4 actuators, right? For the motion of the shake table, you need actuators. These actuators will provide the motion to the shake table. And how much? But horizontal acceleration you can provide up to 1.5 G. This is most important part. 1.5 G. You see, as far as shake table is concerned, these two things are very important: payload capacity and the how much acceleration you can give, right? So basically, it is a 6 degree of freedom. You can program the 2 translation, 1 vertical, and 3 rotations, right? So 6 degree of freedom. This is the world's biggest shake table, right? It is in Japan. This is a shake table in Japan, right? Now you just imagine this, the size of the testing. You see, what is the size of the shake table? 20 meter by 15 meter. World's biggest shake table, right? World's biggest shake table. And what is the capacity? The capacity is 1200 ton. 1200 ton, that is the capacity, right? Suppose we have a shake table in our lab, the capacity is 800 kg or 1 ton. That is the capacity what we have. It is 1200 ton, right? And this is the most important part. and at the same time provide the acceleration like this. This is very important, right? So the maximum extension you can provide is this in x, y, and z direction, right? The displacement is 100 centimeter. 100 centimeter is the displacement you can provide in direction, and the vertical direction 50 centimeter plus or minus, right? And the maximum moment is, I think this is the this is a number you have to appreciate. So this is the world's biggest shake table. Japan is considered to be the best as far as the earthquake preparedness is concerned, earthquake testing is concerned, everything. The Japan has done extensive work in the area of earthquake engineering. As far as India is concerned, the oldest institute, the IIT Roorkee, earlier it was University of Roorkee, and the Department of Earthquake Engineering is there, and they have a shake table. This is a shake table, right? At IIT Roorkee, we have a shake table at IIT Kanpur. We have a shake table at SERC Chennai. Most of the IITs we have a shake table, but there is a variation in the facility. At some places, a very good facility is available, like SERC and IIT Kanpur. A wonderful facility is available for the testing. Now you can see here this is the view of 1/5 scale model of the 7-story RC frame building. 1/5 scale model, right? 1/5. This model is 1/5. So you can imagine which type of structure they are testing, right? Now the question will arise. There is a 6 degree of freedom. 6 degree of freedom means 3 translations in x, y, and z direction and 3 rotations. Now 6 degree of freedom, it will become very difficult to provide, and it will be very costly also. So generally what happens, I'll tell you. You see, as far as the earthquake wave is concerned, right? Earthquake wave. The earthquake wave is generally like this, and if you say this earthquake wave, this wavelength of earthquake wave is maybe a 3 kilometer, something like this, 3 kilometers, right? This is the wavelength of earthquake seismic waves I'm talking about, right? Now if I'm talking about a building, my building, now building dimension maybe 20 meter by 30 meter, or 40 meter by 50 meter. It means my building is situated somewhere here, right? So this building is going to observe, means this building is having number of foundations, and all the foundation is going to observe the same motion, because as compared to the wavelength of the seismic wave, the dimension of our structure is very small. This is 3 kilometers, while here the dimension is maybe 20 meter, 30 meter. It means all the foundations of your structure are going to experience the same motion, right? But suppose if I'm taking a pipeline, for example, if a project of pipeline is there, right? Suppose if this is the project, this is the pipeline I'm talking about, right? So pipeline is basically okay. 1 minute. The pipeline is basically its length is in kilometers, right? Length of the pipeline is in kilometers, right? So if you look at this, then this portion, this particular point, and this particular point, both will experience different motion. It means we have to consider the rotation of the pipeline, rotation component of the earthquake for the pipeline analysis, right? So in case of a long structure, you have to consider rotational degree of freedom also. But for the structure, simple structure like us, which is 30 meter by 40 meter, 40 meter by 50 meter, then you can simply take only the translational component, right? So we consider components are X, we consider delta X, we talk about the delta Y and the delta Z. So this is the deformation in X, Y, and Z direction. But we are not considering the theta X, theta Y, and theta Z. These rotations are not required. These rotations are not required for the small structures like an individual building. It is not required. Again, I'm repeating, the wavelength of the earthquake wave is maybe 2.53 kilometers, and as compared to the wavelength of the earthquake, the size of the structure is very small, and therefore the rotation, if we don't count, it is not going to make much difference. But for the long structure like pipelines, then we have to consider a rotational component also, right? And therefore we are only talking about the three major orthogonal directions. So we talk about the two horizontal component and one vertical component, right? It means because of the earthquake, the shaking is taken place in two horizontal direction and one vertical direction, right? Now the next part is now we have three components, right? We have three components. Which are the components we have? We have a component in X direction. Then the earthquake will shake in Y direction also, and it will shake your structure in Z direction also, right? If I'm saying that if this is my building, and this is my building, for example, okay, then this building will be shaken in X direction, it will be shaken in Y direction, it will be shaken in Z direction, right? So this X and Z, they are horizontal directions, and Y is the vertical direction, right? Now the question will arise, how many components should we take? Either X means to original component of earthquake will take, or all the three, right? Now for that we have to understand the acceleration, right? The acceleration of earthquake, we talk about the acceleration of earthquake in X direction, right? Or we can say acceleration of earthquake in Z direction. These two are horizontal direction, and this is the vertical direction, right? Now what is happening if you talk about the vertical acceleration? Generally this vertical acceleration, when you go away from the epicenter, this vertical component is reducing very fast. The vertical acceleration reducing very fast, right? Near epicenter means near the place where the earthquake has taken place, near epicenter, the vertical acceleration is high. But when you go away from the epicenter, maybe 20 kilometers away from the epicenter, the vertical acceleration is only 0.2 g, right? 0.2 g means 0.2 of means 20% of gravity acceleration, right? Now what is going to happen due to this, right? That we try to understand. Right, now we try to understand what exactly is going to happen for the vertical acceleration, right? This is my structure, right? And now the vertical acceleration is taken place in this direction, right? The shaking is taken place. It means this is actually 0.2 g, right? 0.2 g is the vertical acceleration. So what is going to happen when if I this vertical acceleration will add force to this column, or it will reduce the load on the column. So if I'm talking about uh, a load on the column, then what is the load on the column? Suppose if I'm talking about the column A, for example, this is a column A, so a force in column A, for example, it will be, what is the load? Actually we have the gravity load on this column. Yes. What is the gravity load? Gravity load is, for example, it is W. The gravity load on the column is W plus or minus. Now this will increase the load. It is 0.2 g. This is the gravitational acceleration into the mass, right? So what is going to happen now? This is the load coming on the column is mg plus or minus 0.2 mg, right? So this comes out to be either, now there are two possible values. The one value is 1.2. Load coming on the column is 1.2, or it will be 0.8, right? This is the load coming on the column, right? Now, for how much force we have designed this column? Go back to gravity load. What is the factor of safety we have used? Actual load coming on the column is W, and then we multiply by the factor of safety 1.5. So what is the capacity of the column? It is 1.5. Actually, this is 1.5. This capacity of column A, right? This is 1.5 m into g. This is the capacity of column, right? Actually, this is for the gravity load. And now because of the earthquake, if this 1.2 mg will come, then definitely it will taken care by this column, right? 1.2 mg. This is the actual load coming on the column. 0.8 mg, there is no problem. But 1.2 mg, if it increase, so it is less than the design force of this column, right? So this is very important, that vertical acceleration, when we consider away from the epicenter, the vertical acceleration is very reduced acceleration, and therefore this is not important for us, right? So therefore we are saying that this vertical acceleration is not important for us if a structure is located away from the epicenter, right? And therefore we are designing our shake table for two horizontal components, right? So we have reduced what we have said that the rotation component of the earthquake is not required. Now we are saying the vertical component is not required because your structure is located away from the epicenter. If your structure is located near epicenter, this component is required, right? So we now talking about the two horizontal components, right? So the predominant component is horizontal. Now the horizontal shake table, if you consider, it will give you the horizontal shaking of the ground, right? Now question will arise, now if we want to create a shake table, then the shake table should be a biaxial shake table. Biaxial shake table means it should vibrate in two direction, x and z direction, right? Your shake table should be vibrating in x and z direction, right? Now again, to create a biaxial shake table, it is little bit costly. So therefore what we have said, we say that, okay, what the code is saying, saying that you consider the component of earthquake in only one direction at a time. At a time you consider earthquake component on your structure in one direction only at a time, right? And therefore what we have said, we said that, okay, we are going to prepare a uniaxial shake table. Uniaxial shake table means it is moving in one direction only, in horizontal direction. And what we do, we test the model on it, and then we change the orientation of the model 90 degree. Then we can test the model in the other direction, right? So instead of the 6 degree of freedom, the uniaxial shake table, So uniaxial shake table will serve the purpose, right? So we talk about the uniaxial shake table only, right? Uniaxial shake table. Now these are the shake tables available at LD College of Engineering, right? This is the first shake table developed. I tell you, this is the first shake table, right? This shake table is developed in the 2005, right? Now here the concept was like earthquake engineering subject was introduced. Now there is no laboratory facility at LD College, and therefore we say that without the experiment, it is very difficult to understand structural behavior. So we have to develop earthquake lab, but we don't have the money, we don't have any financial support, and therefore what we have done, actually we are running ME structural engineering program here. So the intake was 18 at that time. So we made 9 groups uh, of two students, right? And we say that you have to, like the one seminar was there, seminar component in their the curriculum of PG course, and we say that in this project SD, sorry, some project component was there, and in project component we say that you have to prepare one model. Remember, one model of structures that we are going to test shake table, but we don't have the shake table. So actually the 9 groups we have of the students. So in each group 2 students were there, and we the 8 groups were allowed the model, and the 1 group was allowed to fabricate the shake table. I told you we don't have any finance support, or we don't have the money at that moment. So what we did, we have used the waste material from our store. So we collect all the waste material like channels and angle sections, everything we have taken up, and then one group was asked to fabricate the shake table, right? And it is given in the month of January, and the deadline were March. And in the March, these students have prepared models and this shake table. This shake table size is 8 feet, 8 feet by 4 feet. This is a very big shake table, and you see, and we have given 10 marks to these students for preparing this shake table, right? 10 marks. So they have done a really good job. This is the first shake table we have developed at LD College without any financial support. Actually we have given a proposal to the Gujarat Council of Science and Technology for this development of shake table and the models, but we haven't received any response from the Gujarat Council of Science and Technology, and therefore we have created this shake table. But what happened then? After some time, after 2 years, we got a sanction from the Gujarat. They said that okay, now we are giving you the grant to develop a shake table. Now at that moment our head of the department was someone else, and I asked that, sir, now we received the grant from the Gujarat, so what should we do? He said that okay, we will return the grant because we have already developed a shake table. Then at that moment मैंने वही बताया कि अगर लक्ष्मी आती है तो उसको वापस नहीं भेजना चाहिए. So we said that we have to use this grant. So basically, the shake table we have developed earlier, it is a very low frequency shake table, and we say that okay, we are going to develop the high frequency shake table, right? And therefore, we have developed another shake table. This is the shake table which is a high frequency, where you can apply 15 hertz frequency, right? So we have developed another shake table with the help of the Gujarat grant, Gujarat Council of Science and Technology, and then you see, our laboratory was inaugurated by a member of parliament, Surendra Bhai Patel. Basically, he is also a civil engineer. When he has visited the lab, he said that Mr. Sanghvi, if you have developed this laboratory before 2001, it will be very helpful because I am able to understand everything here. We have kept our laboratory all Institute of Gujarat. So the students from other institutes are we are also coming to our laboratory, and we are performing the experiment in front of them. and we received a wonderful feedback, and we received a feedback that it is very easy to understand the structural behavior through these models, right? And therefore we have sent a proposal to GSDMA, Gujarat State Disaster Management Authority, Gujarat State Disaster Management Authority, right? We have sent a proposal, and we say that we are going to produce a low cost stake table, low cost, right? Because the costing is high, then they are not going to give us financial support. So we said that we are going to prepare a very low cost stake table, and the models, it is within 5 lakh, 5.5 lakh. And then GSDMA has given a approval that okay, fine, you can develop a shake table. So they have given a grant for the 2 shake tables, and then they said you test the shake tables and then you finalize which shake table we have to finalize, and then we are going to give the shake tables to 18 government colleges, right? This was the project, and then we have developed this shake table, right? And it is costing around 5.5 lakh plus the models we have developed, right? See, this is the shake table which is finalized at the end. It is a 5 feet by 3 feet. This is 5 feet size and this is 3 feet, and this is the control panel we have. So we have a shake table with a random motion, right? It is also high frequency, 15 hertz frequency we can apply here, and actually it is not 25 hertz, it is 15 hertz, and the payload capacity is 500, but we have tested, basically capacity is almost 1000 kg, but we are testing at 15 kg most of the time, and the horizontal displacement is 60 mm, that is the maximum, right? This next part, what we want is the instrumentation setup. We need an instrumentation setup, and this instrumentation setup, we need a vibration analyzer. So we have purchased a vibration analyzer. Now this is a little costly affair. We have purchased this vibration analyzer of 22 lakhs, and these are the sensors, the uniaxial sensor. This sense the motion table and the models we have prepared. So we need to capture the data, right? What is the response of your model that you have to record? So you need the instrumentation setup, but this instrumentation setup nowadays it's available in low cost. You can purchase within 6 lakhs or 7 lakhs. So this is available right now, right? But this is from the France. Oros company is there, and we have purchased that, right? So then we have developed models also. So I'm going to discuss the models after that, but we have created experimental setup where basically we are going to test. Am I audible? Is it clear? Am I audible?
Yes, sir, you are perfectly audible.
Yeah, okay. So basically when you create a model, you know the basic property of all the materials you are using in the model. So the material testing we are carrying out in our laboratory. Then we have developed a setup, experimental setup, to determine the stiffness of the models. Then we perform an impact hammer test, free vibration test, and shake table test. I will explain all this test, right? So this is the determination of the stiffness of the model, right? This is a frame. You can see this is a frame, right? This is a frame, and this is a frame where we are testing the model. So suppose this is the model. This is the model where we actually calculate what is the real stiffness of the model. So how we perform the test here? We are applying the force on the ground story, right? It will give the stiffness of the ground story. Then we are locking the first story and apply the load on the second story. It will give the stiffness of the second story. This is the real stiffness of your. You can compare with the theoretical one, right? So you see, this will give you the actual picture, right? So this is the setup. Now we start the test, right? So we go for the free vibration test. The free vibration test, I told you it is of two types. One is the initial displacement. You disturb the system by the displacement, and then you are relieving. Now your system is elastic, so your system is going to vibrate, right? Now we are knowing that this is right. This is the acceleration curve, right? And I think this is the one cycle of vibration. This is the one cycle of vibration, right? Peak to peak. So time required to complete one cycle is known as a natural period of the building, right? Now this is also T, right? This is also T. This is also T, right? So this is the natural period of the building, I tell you, right? And the natural period will remain same. It is going to vibrate. This T will remain same, right? Damping is there. Damping is there, and therefore this displacement is reducing, right? Displacement cycle by cycle is reducing because it is a free vibration, right? So this is the acceleration. Here is higher maximum acceleration, and then because you see you are performing free vibration test, means the maximum disturbance at initially, so you get the maximum response initially, and then your response is keep on reducing from cycle to cycle, right? So there's a reduction in the response, right? So this is when you connect this, it will be like this. This is known as a envelope, right? So it is keep on reducing, right? So this is a free vibration test we perform, and then we measure the acceleration and time, right? And this is the you see from this test what exactly you are concluding, because in cycle to cycle the amplitude is reducing means damping is present, and therefore you can measure the damping means how much energy is absorbed in each and every cycle. So this is the equation which is given from the book of A.K. Chopra, Structural Dynamics by A.K. Chopra. So you can use this equation where we are talking about the acceleration in two consecutive cycles. Right. Now how we perform you see now the testing is started, right? So first of all we see how the free vibration test is carried out, right? This is very important. We'll see. Now look very carefully, because this is very interesting. Before I start this, I'll tell you. You see, when we were studying, and when the professors are explaining that your structure is going to behave like this during earthquake, at that moment we have to imagine that how the structure is going to behave during earthquake, right? And what professors are explaining, we are believing, and but you see, it is very difficult to understand the structural behavior, right? But then at that moment when we are working in earthquake lab, we for the earthquake subject, we find that if we develop a setup, then easily you can see the behavior of the model, right? And then your model will speak on behalf of you, right? Your model will speak. There is no need to explain anything, and the student can understand from your model only, right? So this is a model of structure. You can see this is the floor, one floor. This is the base, second floor, and this is one of the base plate. You can see that it is the 3-story structures, and then this is the sensor. This is the sensor placed here. Right? Sensors are placed here to capture the response of your model, right? And the sensors are connected with the data acquisition system, and this data acquisition system is connected with the computer. So you can log all the data, right? So we are performing the free vibration test. Now what is the free vibration test? You can see very simple test, right? Very simple test. This is the sensor. This is the uniaxial sensor we have placed in one direction. So at the top story, middle story, first story, right? Now what exactly we do? You see, what he is my student, and right now he is a professor at another engineering college, right? Now again, I want to explain this. Look at this. What he is doing? Look at this again. He is disturbing. He is disturbing the model, right? He is displacing and then relieving, right? Again, I'm repeating. Look at this. He is disturbing. He is displacing the model by certain amount, 10 mm, 20 mm, 30 mm, right? And then you see he is releasing. Now your model is having some elastic property. So on the basis of that, it is vibrating, right? So if there is no constraint, then your model is going to vibrate in its natural mode. Again, I'm repeating this because this is very important to understand, right? Here he is disturbing, he is giving some displacement. So this is the free vibration test with the initial displacement. The system is vibrating, this model is vibrating, right, because of its elastic property, right? And as we are not interfering with its vibration, then it will vibrate in its natural mode, right? Suppose if your father is saying that okay, you want to you can do whatever you want, then definitely you will do the things what you like. The same way our structures, when there are no constraints, then they vibrate in the natural mode, right? So again, I'm repeating this test. This is a simple test, is a free vibration test, and the structure is vibrating and the sensor is sensing the response, and it's taken here. This is the computer and acquisition systems, and it is recorded there. You can see is the record also. These are the sensors and these are the wires which is connected with the data acquisition system. This is a data acquisition system, and you can see here this is the response we received, right? Now there's a reduction in the amplitude. Look at this, and this is captured, right? So we can use the equation what we have. This equation we can use, and we can find out damping. What is the damping present in the model? And as far as the steel structures are concerned, a 2% damping is considered. 2% of the critical damping, right? In RCC structures, 5% damping, and in masonry it is 8%, right? So damping is actually least in the steel structures, and then 5% in RCC and 8% in masonry structures. Right. Now the second is the impact hammer test. The second is the impact hammer test. What is impact hammer test? This is a hammer. This is a hammer. This is not an ordinary hammer. Here, this is the tip of the hammer where the sensor is there. Right, sensor is there, and basically this wire is connected with here, right? And this hammer is connected with the vibration analyzer, data acquisition systems. It is connected, and then what we do here, we are applying the impact. This is the, you see, we are not disturbing this model right now by displacement. We are not giving any displacement, but what we are doing, we are applying impact with the help of this hammer. So this hammer will give impact here, right? It means it is not the initial displacement. Now it is the initial velocity. We are giving the initial velocity, right? So this is known as the impact hammer test. Now sensor is here. So the sensor will sense how much energy is given to this model, right? And then this model will vibrate. This model will vibrate. Okay. So now we will see how the test is performed. That we'll see. Impact hammer test, right? Now, yeah, you can see the says a faculty member here in our department, and these all are ME students. These all are ME students. At that moment, she's also doing the masters. So these are the ME students, and you see, you can see the smile on their face. You look at the faces of these students, how they are enjoying this experiment, right? Now you can see this is the impact hammer. Impact is given. Now the system is vibrating, right? And it is start recording there, right? So this system is going to vibrate in its natural mode. So you can get a natural frequency of this model, right? This is a spring mass model. This is a spring mass model. right? So you get the natural frequency, you get the period of the building. What is the natural per unit time? Number of cycles of vibration per unit time, right? That is the natural frequency of the building. And natural period means time required to complete one cycle of vibration. And the damping means, you see, when you apply the impact, then your system start vibrating, and again it will come back to rest after some time. So it means some energy is absorbed. This energy is absorbed by means of a damping. Damping basically it's the inherent friction which is present in the system, right? So the three things are very important. One is natural frequency of the building. Then the second is natural period. Natural frequency and natural period, they are inverse of each other. And the third is the damping, right? So again, I'm repeating this experiment. This is the impact hammer test, where we disturb the system by applying the initial velocity. There is no initial displacement, but initial velocity is there. And then we measure what is the frequency of vibration and damping present in the system, right? This is what we are doing. Okay. Now we go for the shake table testing, right? Shake table testing means we are putting our structure on the shake table and we apply the variable frequencies, right? And we measure the response. This response, you see, we are measuring the response in terms of acceleration versus time, right? Basically, earthquake is a dynamic force. So with time, this acceleration is changing, right? So we are measuring response in terms of the acceleration versus time, right? And then we also draw the frequency response curves also, right? We'll see that what actually. We can also determine the natural frequency of vibration, at the same time natural period also. Both can be determined from the frequency response curve. For example, this is a single story building, right? Single story building means we have a single slab, right? So at this level we have a slab, right? So a heavy mass is located at this particular level, and it is supported on the walls and the columns, right? Supported on the walls and columns. Okay. It means this is a heavy mass. This heavy mass is supported on the column. It means if we create a mathematical model, we can say that this is a heavy of the slab. Now this is a heavy mass. This is the column. The column is having certain stiffness. So this is the stiffness A. All right. And in this system, a damping is present, right? The friction is always present in your system. So basically, a damping is always present, and this damping you have to consider like this. This is the dashpot, right? So this is a mathematical model. This is the mass which is going to move in horizontal direction. So it is moving in horizontal direction. This force is applied, and it is connected with the column, and this is the damping present. And therefore, if you draw the free body diagram, it will be like this. This is a free body diagram. And then if you analyze by any structural engineering means, you can analyze very easily. So if you want to determine the frequency, what is the frequency? The circular frequency is square root of k by m. The k is the stiffness, right? M is the mass, k by m. So what is the frequency? The frequency is natural frequency 1 upon 2 pi square root of k by m. The unit of this is actually radian per second. The unit of this is radian per second, right? This is radian per second, and the unit of this is cycle per second. This is cycle per second, right? Now here you have to understand this natural frequency. This is the natural frequency. It depends on two parameters, k and m. Now mass we are knowing. Now the k, what is k? The k, for example, if it may be a 3 a by a cube also. It depends, right? It depends. What are the support conditions, right? It may be a 3a by L cube, but it depends on what? It depends on E, modulus of elasticity. It depends on moment of inertia. It depends on the height of the columns, right? So we will see then. Therefore, the first models we have developed is the spring mass model. Spring mass model, right? Now this spring mass model is what exactly? This is the spring mass model where heavy mass is located at the top. This will represent the slab. This will represent the slab, right? And this is the column. This will represent the column, right? So this is basically a single story building, right? This is a single story building where the heavy mass is located at the top, is supported on the column, right? Now, preparing the spring mass model, this is a very basic model. And what we said that your frequency depends on how many parameters? It depends on mass, it depends on elasticity, it depends on moment of inertia and the height. So we prepare four models. We prepare four models to study the effect of individual things. So we said that we change the material. If we change the material, it means we are studying value of E. What is the effect of E on vibration? When we change the height of the column, we are saying that some columns are having the height 20 feet, other columns are 10 feet. Then what is the in the behavior that we have to study? We change the mass, right? So here we study M, here we are studying L, and in the thickness we are studying the moment of inertia, right? Moment of inertia. So these four components we are studying by making this four models, right? So this is the first model where we are talking about spring mass model with a different material. Now this is made up of stainless steel, this is the flexi ply, this is the brass, this is the copper, right? So we have made it, and the mass is remained constant. All other parameters are constant. You see, mass is constant, height is constant, right? Only change is cross section is also same. Only changes its material. So we are only studying what here we study. We want to study the modulus of elasticity, right? Suppose if I'm making my structure with steel, then E is different. If I'm making my structure with concrete, the E is different. If my vertical elements are made up of wood, the E is different, right? So which material you're using in your structure, maybe steel, RCC, wood, then this value of E will change, and we are right now studying what is the effect of E, right? So we have performed a test, and then we get a graph of time versus acceleration. This is the acceleration, right? This is vertical. This y-axis is the acceleration, and horizontal is the time, right? So we perform a test. Up to this only, right? And this we get the result, right? And we received for the milestone. If we prepare a graph of acceleration frequency, then what actually happened? You see, when we draw a graph, you get a one peak. Now this one peak is nothing but this is the natural frequency of the vibration. This is basically frequency versus acceleration curve, and this will tell you what is the frequency is around 3 hertz, right? Milestone. This is for the stainless steel. This is the peak you have received, and it means this is the peak you have received. It means this is the frequency of the stainless steel model. This is the frequency for the flexi ply, right? So now we perform the test, right? So just we perform the test so you can understand it properly what is happening, right? And now this is the most important test, I tell you. Here you can understand the concept of resonance, right? What is resonance, right? Now here you see we are knowing that the frequency of this model is different, frequency of this model is frequency of this model. So frequency of all these models are different. Some models having low frequency, some models having high frequency, right? Frequency we have said it is 1/2 pi square root of k by m. So the frequency is different for all the models. Now, when we test it, now we are applying the shaking. We are applying the shaking, right? When we apply the shaking, what is happening? You see. Now, watch carefully, right? What happens to all this model? You see, we have placed all the models on one platform, and then we are giving the same motion to all the 4 models. Motion given to all the model is same, right? We'll see now what is happening. All right. Now you see the same motion is given. Now these 3 is not responding, but only the first one is responding. This is responding. Now what is the reason? The reason is the shaking frequency is matching with the frequency of this model, right? So frequency of shaking is matching with the frequency of the system. This phenomena is known as resonance, and during resonance a large displacement is observed, right? So again, look at this behavior. So the first is response. Now what I'm doing, I'm increasing the frequency. I'm increasing the frequency of this shake table, right? Then what happens, you see, right? So I'm increasing the frequency. When I increase the frequency, now the response of that system come down, because the frequency of that building is not the first one talking about. The frequency of the first one is not matching with the frequency of the shake table. So the response come down. And now what happens, you see, if I increase the frequency, then now the frequency of shake table is matching with the frequency of the second model, is a flexiply. And now see, you see, other 3s are responding, but the model with the flexiply is responding because the frequency is matching, right? And then we still increase the frequency. What is happening, you see again. This is a very classical example to understand the resonance, right? Now if I increase the frequency, again the first 2 models are not responding. Now the third model starts responding because it is having high frequency. I increase the frequencies, of frequency of shaking matches with the frequency of this model, right? And therefore you see, look at this, the response in resonance, you get an enlarged response, right? Now still I'm increasing the frequency. Now what is happening? Look at the behavior of the 4th one now, right? Again I'm repeating, the same motion is applied to all, right? And here the sensors are placed at the top. Sensors are placed, so it is sensing the motion. It's sensing the response of your model, right? So this is a very simple experiment, right? But all doubts will be clear as far as students are concerned. The student will easily understand what is resonance is, right? Now my question to you is, which type of building is affected during earthquake? High rise or low rise? Or the steel building or RCC building? Which type of building will be affected? Now the question is obvious, that we cannot say which frequency are carried by the earthquake, right? It depends on that. So if you're you see, we are constructing our houses. Once we construct our houses, is natural frequency is fixed, right? Now if earthquake carries the same frequency, then our structure is going to vibrate more. It will enter into resonance then, right? So therefore it is not our in hand that we can change our frequency of our structures, right? So when we construct our structures, the frequency of our structures are fixed, and then earthquake will come. And when the earthquake will come, earthquake carries certain frequency. If this frequency matches with your structure, then it will enter into resonance. And if it enter into resonance, then your structure is going to observe maximum damage and maybe the collapse. This is the reason, right? So this is the importance of the resonance. Again, you see here, right? So you have to observe this experiment again, right? Again, you see, because this is very important from the resonance point of view, and you cannot say my steel structures are affected, my RCC structure will be affected due to this. Again, it depends on the frequency carried by the earthquake and the frequency of your structure. If both will match, then larger response of your structure will be there, right? You see, the low frequency, the first model is responding. If I increase the frequency, again Then this next model is start responding now, right, with the increased frequency, right? And then if I increase the frequency, the third model starts vibrating. If I still increase the frequency, then the fourth is start vibrating, right? So you can understand resonance correctly, right? Okay. So basically what we do here, you see, we have performed the test on shake table and we get these frequencies. These frequencies we received for mild steel, stainless steel, flexible and glass. Then we have also modeled this in the STAD, and in the STAD software we received these frequencies. And theoretically, because we know mass, we know the stiffness theoretically, so we calculate by putting in the equation and we get this answer, right? Then the second model is the height, right? Now here sometimes our column height may be 20 feet. Here we have a column height, this is suppose L or 2L we say, then this is L, right? This is 1.5 L. So if the height of the column changes, then stiffness of this will change. Stiffness of all model will change, and then we get a response. If height is this, if height is more than frequency is less, right? And if height is less, frequency is more, because it's 12 EI upon L cube, it is in denominator. So if L will increase, frequency will reduce, right? So length will increase. So again we perform the test. This is from the software, this is from the theoretical. Almost they are matching, you see, they are matching, right? So this will give you confidence that okay, what we are doing is correct. Then we have performed a test on the spring mass model, in which different mass is there. So here you can see here mass is less, then we add the mass here with the putting the collar here. Here this is again increased, this is again increased, and we test it, and then we get these results, right? Now we are not discussing the results because the results we just try to understand the behavior, right? Then we have the last model is a variable thickness, and we get the answer, right? Then next experiment, we are not talking about a single story building. We talk about the 3-story building. This is the first story, second story, this is the third story, right? So this is the first, second and third. We are talking about a 3-story building, right? And we have prepared a model. Right? Now you see what exactly we did. We try to develop a model which are flexible, so it can show you a larger response. Such kind of response you cannot see in the real structure because it is little stiff. But we have to magnify the displacement, and therefore we have prepared a flexible models, so you can see the behavior very correctly. So here what we have done, this is the first floor slab, second floor slab, this is the third floor slab. So it is a 3 degree of freedom system. This is a 3 degree of freedom system, and we try to develop a 3-story model. And you see this model is analyzed in the STAD software, and we get the mode shape. What is the mode shape? Mode shape is a deformed shape. When you apply the frequency, then I think you have studied the mode shapes, right? Mode 1, mode, it is a 3-story building. So basically 3 modes will come in picture. Right? So this model, 3-story model is modeled in software, and we get the mode shape. This is a deformed shape. Now this is the lowest frequency. This is omega 1. You get omega 2 here. This omega 3, right? So it is the 3-story building, so you get the 3 frequencies, and this is the lowest frequency. Omega 1 is the lowest frequency, which is known as a fundamental frequency. And fundamental frequency, what is happening? Your all masses, this is the mass 1, mass 2, mass 3, all are moving in one direction. Right? This is very important, right? All masses are moving in one direction, and therefore these masses are giving maximum contribution, right? Maximum contribution. Our code is saying that in case of multi-story building, you have to carry out the dynamic analysis up to 90% mass participation. This is what the mass participation is, right? So we have to talk about a mass participation, right? This is the mode 1, and in the mode 1, how will you identify mode 1? You see, this is the equilibrium position, right? This is the equilibrium position, and this is a deformed shape, so it is integrating only once here, right? Equilibrium position and the deform, it will only intersect at one, so it is the first mode. Now here what is happening? It is intersecting here and it is intersecting here. These are the two intersections. So this is the mode 2, and here this is the mode 3. How do you identify? This is the first intersection, second, and this is the third, right? So the three interactions, right? So this is the third mode. Now we'll check exactly what is happening. We take the right. Now here you look at this. The height of this first story is more as compared to other two, right? It means height is more, means this is flexible story. This is flexible story, right? Now it is a flexible story, then larger deformation will be there only, right? Okay, so we will see the larger distance at the ground story, right? Because it is flexible. Now look at the response. Am I audible? Hello?
Yes, sir, you are audible.
Hello? Am I audible?
Hello? Yes, sir, you are audible.
Yeah, okay.
Yeah.
So you can see here, the ground story is flexible, and therefore you can see a larger response will be here, right? On the ground story, larger response. Upper two story is having less response, but total deformation is there, but the maximum response is here, right? Just wait for a moment. Contact okay. If you look at this response, now you see frequency is increased. Again I'm saying, you see, look at this. At the low frequency, all the masses are moving on one side. All masses are moving on one side, right? This is the first mode. Now when I increase the frequency, you see the deformed shape is changed. Now your structure is responding in a different way, right? Responding in a different way now. Okay. So this is the second mode, third mode, something like that, right? So your structure is going to respond differently with the different frequencies. Again, I'm saying again, this is the lowest frequency I'm supplying, and when the lowest frequency, it is all the masses are moving on one side. So this is the first mode, right? But when I increase the frequency, look at this. It's a deformed shape is changed, right? Your structure is going to behave like this during earthquake. So that's why we are saying it's a complex behavior. You have to understand it properly, right? Now you can see this, right? Now response is reduced now, right? At the higher frequency, this structure is not responding, right? So therefore we are saying that okay, always if high frequency earthquake will come, our structure will be affected. No, If your structure is a low frequency structure, then high frequency earthquake is not making any sense. It is not going to disturb your system to great extent, right? So now then look at the second one, right? Now here what is happening? The height of the second story is high, right? Second story. Now look at this. Now I am starting the vibration with the low frequency. With the low frequency, the system is vibrating, right? Look at this, right? Maximum deformation is on this story, right? Not here, not upper story, but maximum deformation here. Right now, if I increase the frequency, again shape is changed. Look at this. It is vibrating in the first mode. Now it is vibrating in the second and third mode. Right? Second and third mode. What is second and third mode? I told you earlier. This is first mode when all the masses are moving on one side. Second mode, some masses are moving in one direction, other masses are moving in opposite direction, and this is the third mode. Right? So here understand this part, and this is the last. Now here I added some mass at the top. If I add the mass, what is going to happen now? If I add the mass, the frequency is 1 upon 2 pi square root of k by m. If I increase the mass, frequency will come down. If frequency will come down, then at the lower frequency it will vibrate. Very low frequency, right? Now look at this. You have to understand this again. What is the effect of addition of the mass? If mass is added, then frequency reduced. Now you see the response. If I reduce the frequency, this is how it is going to vibrate, right? So always we feel that seeing is believing. आप जो देख रहे हो उसके ऊपर आप विश्वास करोगे जरूर, है ना? So look at this. Here you can see the shape is changed if I increase the frequency, right? So this is very important for us to understand the structural behavior. Again, I'm saying structural behavior because of earthquake is very complex, but we have to understand that, right? Look at this. At the low frequency, it is vibrating in the first mode, right? You see, this is what we have captured in the photograph. Here, all the masses are moving on one side. You can see this 1, 2, 3 masses, right? They are moving on one side. In the second, you can see this mass is moving in this direction, while this mass is moving in this direction. It may be a second or third mode. This is a 4-story structure, right? And look at these students, right? The students are taking advantage of these facilities available at the laboratory, right? Now, then we calculate the frequency and everything we calculate. Then we talk about the deficiencies in the building. Open ground story, vertical irregularity, stiffness irregularity. Yesterday we discussed open ground story structures. Now, open ground story structures, we say that open ground story structures, the maximum deformation is concentrated at the ground story, right? Ground story. And upper part will remain stiff, right? And then in Bhuj earthquake, almost 90-95% buildings are collapsed because of this soft story effect, right? We said they say working as an inverted pendulum, and such kind of damages had been observed in the structures. Already we have observed this, and now we will see the soft story effect, right? We will see the soft story effect. What is the soft story, right? 1 minute. Okay, you can see this here. What we have done, we have placed a shear wall here. It is a steel plates we have placed, and on the ground story there is no plates. It means the stiffness of these 2 story is high as compared to the ground story, right? And then we perform the test. Now look at the behavior, and now when you look this behavior, you understand what will happen in soft story. Just look at the behavior. Look at the behavior. Look at the deformation at the ground story as compared to the upper story, right? Look at this. Now this students are testing in our lab. Our lab is for the students. by the students, right? And they are free to test with all the facilities. Look at this. Now, upper story are moving as a rigid body, but the deformations are at the ground story. Look at this deformation, right? If you continue with this, it might fail, right? Then this is a soft story failure. When structure fails, definitely it gives us a lot of pain. But when the structure fails in the laboratory, we become so happy, right? Now you have to look at the faces of the students, right? Faces of the students here. This is a 1 minute. Right, now we see this is the soft story. Now here you can see the failure also. Now you see this, these are the students, master students. Some of them have joined the road and building department, some of them are the professors in other colleges, right? Look at this behavior. The upper two story are stiff, ground story is flexible, it is a soft story, right? Now here you can see larger deformation in the ground story, right? Now this student will never forget, right? This student will never forget this experiment during their life, I tell you. You can see this is gone. This failed. This column has failed, right? And look, the person here is clapping, right? He's enjoying. Look at this. There are smiles on the faces when structure fails in the laboratory, but it don't give you any smile when it fails in the reality, I tell you. So this will tell you a lot of things, right? And here when it fails, a lot of energy release. Now this portion is very hot, I tell you. When it failed, it is very hot because number of cycle perform here, right? Now you can see these students will never forget this soft story failure in their life, right? I want to just mention regarding this person. This person is Jigar Rana. Jigar Rana, who has fabricated this shake table, I tell you, as a student. So the whole credit goes to Jigar Rana for fabricating the shake table. And this is the first shake table we have developed at LD College. Right. Then we measure the acceleration, everything we measure. And you look here, you see total displacement is 40 centimeter, 40 mm at the top. Out of this 40, 30 is observed at the first story, equal soft story, right? So when you interpret the result, you get the answer. Highest deformation, 75% deformation is at the ground story, and therefore the columns are supposed to fail there, right? Then we place the asymmetric shear wall. Asymmetric shear wall means now here we have placed a shear wall, this steel plates on the one side, not on the other side. Now what is going to happen, you see, this is asymmetric shear wall. What will happen? Look at this. Torsion is introduced. You see, you can see the torsion in your building, right? So sometimes we place the shear wall on the back side and we make that part is stiff. So this part is very stiff and this is very flexible. So this torsion is going to come in the picture, right? This is very important, right? Look at the torsion. So you see, during earthquake, we are not able to handle earthquake force properly, and therefore I request you, don't do it. Make your structure symmetrical, and then the torsion can be avoided. Otherwise, earthquake force plus torsion both will come, then it will make your life miserable, I tell you. Right? Okay. Then we get the result, and then we measure. We get, you see here what is happening now. We get the acceleration in both the directions, in x direction and in the z direction. This is z, this is x direction. So generally it is a uniaxial shake table. So we should get acceleration in one direction only, but now we are getting in two directions, right? Now bracing system. Bracing system, we will see what is happening in the bracing system. This is also important. Where you can see the behavior, right? This is a very simple model. Bare frame we are testing. The slab is resting on the column, right? And we are testing this. Look what will happen. Look at this. This is gone. Right? This is gone. Column is gone. Is broken. Right? We will see the next with the bracing. Right. Now look at this. The bracings are placed. Bracings are placed. Right? And when we test it, now the bracings are very thin, and we have placed it, and what is the effect of this bracing we want to study. And when the is going on, you see now your structure is quite safe in this case, right? Because in increased stiffness, deformation is reduced, so your structure is safe. And then we have the third video of the combine. Now you will appreciate this video, right? This is a very good video where we are comparing these two buildings without bracing and with bracing. And now look at the smile on this face, and look, this student is working here, but when the experiment starts, he's observing this experiment, right? So this is the advantage of laboratory where you are working. Now you see, look at this student also. Now, yeah, he's able to understand that without bracing, deformation is high. With bracing, deformation is quite reduced, right? This is what you can understand through laboratory experiments. These are the very simple experiments you can perform at your at your institute also, right? Then we talk about pounding, right? We talk about the pounding. When the two buildings are close to each other, they will hit each other, right? And this is what we have observed in the last lecture. So we have created models without pounding of slab with column, pounding of slab with slab. So they were very simple models. Here, this slab is hitting the column. This slab is hitting this column. While here, the slab is hitting the slab. These models we have created, and look at this. Look at this. What is happening now when the two models are close to each other? When the separation gap is not there, then these models are going to hit. The slab is going to hit the column, right, of the other building. We have designed this column for the earthquake force, but not for the impact. And now we'll see what is going to happen, right? So you see, larger impact force is here, and so these columns will absorb the damage, right? So this you can see here, right? Look at this. It is hitting. Both are hitting each other, right? Now the stronger will survive, weaker will absorb damage or collapse, right? So this is the slab to column pounding. Slab to column pounding, right? Then we have pounding of slab to slab. Slab to slab. Right, look at this, the slab is other slab, and when the experiment starts, you see lot of noise is created because of this impact. Right, now you can see the slab is hitting the slab. Right, this is less dangerous as compared to the slab hitting the column. Right, slab hitting the column. Okay, this you can see. Right, so as such, there are so many videos we have of the testing. We have we carried out testing for last 15 years. We have more than 200 videos for this, right? And then we calculate the peak acceleration displacement, right? But here you see, this is very important because of the impact. Additional impact force comes in. This is due to the pounding. Maximum force is the pounding. When it is hit, give the force. This is the force because of pounding, right? And here you can see in the data also you get the impact. This is the impact, right? These are the impacts on the. This is the motion of the shake table. These are the impact. This is the recorded response of the sensor of the one building. This is the second building. So you get the impact all the time. And again, you can have this force. Again, additional force will come in picture. If your structure is not able to take this force, it will collapse or damage. Right. So gap you have to design. We said yesterday, and the gap to be designed. So here, I think there are many more videos we have. If time permits, then we will discuss in the other sessions also. So there are n numbers of videos we have, and we'll discuss those portion and everything. We'll discuss in the coming lectures if time permits us. Right now, I think we will take a break because it is only 11:42, and we have to start the session, next session, around 12 o'clock. So I think we have to stop here. Right. Now, can anybody tell me, means if any question is there, you can free to ask the questions, please. If anybody is there, yes. Please unmute. Bansal sir, please unmute. Qureshi. Hello. Bansal sir. Arun Kumar. Yeah, please ask the question, please. Hello. You can ask questions, please. Am I audible?
Yes, sir, you are audible.
Yeah. If you have any question, you can ask, please. Because we have to start the new session also. So. Is there any question?
क्लियर है ना? तो ये कुछ बेसिक्स जो है तुम्हारा एडवांटेज है विंडोज का. नो क्वेश्चन सर. यहाँ तक में किसी को इस तीनों पॉइंट में किसी को कोई
no question. Okay. Arun Kumar, you have any question? Arun Kumar.
Sir, if you are not able to unmute your mic, then you can.
जो होगा मेरा बे विंडोज. नेक्स्ट जो टाइप का विंडोज है वो है मेरा बे विंडोज. BAY बे. अच्छा ये
Yes, testing is the best way to learn. That is a comment made, right?
Sir, good morning. Sir, I am Praveen Nigam.
Yes.
I have one question, sir. We
Yes,
generally
please.
design a building for a bare frame,
Yeah.
but in practice, there are lots of wall in a
Yes.
particular housing project.
Yes. Yes.
How it will affect our designing, which we have done for a bare frame?
Yeah.
It will affect more, or sir, it
You
will
see.
in something limit.
Yeah. That's what I'm saying. You see, when we design our structures as a bare frame, and we are putting the infill walls for the functional purpose, right? So as far as gravity loads are concerned, your structure is okay. But during lateral force due to earthquake is concerned, what is going to happen? These columns are going to deform, and the wall infill walls are in between the column, so it is also supposed to move, right? So it is also participating. Uh, and what is going to happen then? You see, additional wall is there, so stiffness is increased. Now with the stiffness is increased, so when the in the initial stage, when earthquake force walls, right, walls, it is shared by the walls and the columns, right? So the stiffness of your structure is increased, and so if you are assuming my structure is having a low frequency, but actually the frequency of your structure is high, right? And therefore the walls and columns both are participating, and then once your wall will fail, then then what you have assumed that is a bare frame, that will come in picture, right? So in the initial stage, what you have assumed, it is not going to work, right? And behavior of your structure will be something different, right?
Sir,
Sir,
but
can I ask the question now, sir?
placement of masonry is like 2 side, 3 side only. This will cause torsion or change in stiffness in any direction or
Yes,
any flow.
because you see, you are providing the opening on one side, you are providing the full wall on another side, so there is a difference in the stiffness, and there's a difference in the stiffness. So one part will become stiff, and another is become flexible, then it create a torsion, right, in your building.
Sir.
Yeah, please.
Sir, can I ask the question now, sir?
Yes, please.
Sir, where we can have the ground acceleration data, sir? Where we can get that data?
There are a number of sites we have. I think I will post you these sites, so you can download the data from those sites, right?
Can we mention in that site with the peak ground acceleration?
Yeah, basically the various components are given. And in that you can have the maximum acceleration, which is a peak ground acceleration. You can have,
Yeah.
right? When you see, it is very simple. The data is given in terms of acceleration versus time, and when you plot it in the Excel, you get the peak, and that is the peak ground acceleration that you easily locate, right? So you need a numerical data, right? And I will mention those sites where you get the data, right? Or if possible,
Yes,
I will share some time history also, right?
Sir, I need the time history data only, sir. That
Yeah,
too
yeah.
for a particular peak ground acceleration.
Yeah. We have certain time history, so we will share with you, right? During
Sir,
this one, right?
specify that particular
Sir, are you
ground motion data. If it's available with you, can give.
Pardon?
If I specify the particular ground motion data, so that can you fetch me that particular ground acceleration data for me?
So if it is available, I will share. You can put in the Telegram group. I will try. Right?
Yes, sir. Thank you, sir. Thank you.
Yeah. Thank you, Kumar. Any more questions?
Sir, please float the name of site in Telegram group.
Yeah. Sure.
Thank you.
If there is no question,
Hello.
then we
Yes, sir.
stop here. Yeah.
Sir, is there any standard provisions that is available to use lightweight concrete in the case of earthquake elements, sir?
Codes.
Codes or any standard provisions?
I think basically the earthquake codes are saying that you light, but you have to refer those codes related to concrete, where lightweight concrete uh, details are given, right?
Because
So
what's my
as
doubt is with
yeah,
respect to the reduction of the density of concrete,
yeah,
the strength will also be minimized. That's a fact. And
yes.
with the combination of this type of concrete in dynamic reinforcement, how it will behave, such a doubt is there.
You see the lightweight. If you make your structure lightweight, it's always helps in earthquake, right? But if the strength is reducing, then there is a problem, right?
Hmm.
So you have to be careful about that. The strength reduction, or suppose your structure instead of ductile, it become brittle. That also you have to observe. So when you are changing the material, you have to be very careful, because
Yes.
in the normal loading, it is not a point of concern for us. But for earthquake, it gives mm, the different types of results, right? So you have to be very careful.
Yes, sir. Maximum the intensity of the earthquake is raised due to the concrete only. Is it no, sir? Maximum damages are occurred due to the fall of concrete over the people, or the damages are maximum
Uh,
cost that only.
Uh, yeah, you see, the damage is taken place in your structure. It's a steel structures or RCC structure. It depends on the frequency of earthquake and frequency of structure,
Yes, yes.
right? So you see, you cannot say it's because of concrete only. It is going to taken place for all type of buildings, right? Because
Yes,
right now we are constructing RCC building
yes,
maximum.
while considering RCC only, I
Yeah.
am telling, sir.
Yeah. So as far as we are going for RCC building, and therefore we are observing most of the damage in RCC building, right? And therefore I think it is our perspective.
Okay, sir.
Yeah.
Such an experiment only I am going to handle out. That's
Yeah.
why I am searching for that kind of notes now. That's why
Okay.
I asked you.
That I have to check, because
Okay,
right
sir.
now,
Okay.
right?
Okay, sure, sure.
Yeah.
Thank you.
Thank you. Anyone else?
Sir. Hello, sir.
Yes, please.
This is Sanghvi Matthew. I would like to ask you a question.
Yeah.
Sir, is it possible to test seismic isolators using this setup, like shake table test?
Pardon?
Is it possible to test seismic isolators using shake table?
Seismic?
Isolator, base isolator.
Yes, yes. Isolator you can test. Okay, I'll show you one video of base isolation. I think this is the last video I want to show you. Just look at this. This is, I think, really wonderful. So you can appreciate this. Just look at this video.
Okay, sir.
I think I have one video of isolator also. Yes, it is there. Can you see my screen?
Yes, sir.
Yeah. Now look at this video, right?
Okay.
It is very simple system we have. You see, we just want to understand the behavior only. So we have to create a model of the isolator, and we placed a roller isolators, right? Look at this. He is Professor PG Patel. He is our co-coordinator, right? Now you look at the behavior. You see, this is the superstructure, right? This is a superstructure, and these base isolations are placed at the bottom, right? This is the base isolation systems. And now look at the behavior. Look at the behavior.
Okay.
Now it's shaking, but the energy is not transferred to the superstructure. isn't it?
Yes, sir.
Again, you can see there's the high frequency vibration is there, but it is not entering into your superstructure, right? It is isolated here, and you can test. You can perform any experiment, right? It's absolutely, yeah.
Okay. Thank you.
Okay. So we stop here because now the second session is supposed to start. We'll take your questions later on. My half presentation is still remaining because a lot of videos are there. If time permits, definitely I will share with you. Right? Thank you. So we stop here, and we take a 5-minute break, and we'll start the next session. Thank you.
Thank you, sir.
Thank you, sir.
Yeah.
Thank you so much, sir. Thank you for sharing this immense knowledge of worldwide as well as ground level knowledges among us. And of course, different contexts, different situations and techniques for the same. And yeah, the experience of faculties and students in the working in the laboratory was really good. It was all really informative and it was all really informative and helpful to us. Thank you.